Hi, so today we're going to be talking about null hypothesis significance testing, which is often abbreviated as NHST. We're going to talk about what these different words mean, and then we're going to apply it in terms of running a Pearson correlation by hand. So our first step in terms of null hypothesis significance testing is to state our hypotheses. So to revisit what a hypothesis is, consider that when we're using statistics, often we're using it as part of a research study to try to answer some sort of research question that we have. The hypothesis is, up front, what do we think is actually going to happen? What do we think is happening in our whole population? We're only going to get a small sample from that population to get the data, but we make some sort of hypothesis about what we think is happening in the bigger population. Now, in null hypothesis significance testing, we really focus on two different hypotheses. So we focus on primarily the null hypothesis, which is abbreviated as H sub 0. And we're going to talk about the alternative hypothesis. And that is sometimes abbreviated as H sub 1, but more commonly you'll see it as H sub A. So the null hypothesis is the boring hypothesis, the one that nothing interesting is happening. There's no relationship between our variables. There's no difference between these groups on our dependent variable. Nothing interesting is happening. So for correlation, this is really that there's no relationship between the variables of interest. No, nothing to see here, nothing interesting going on. There's no relationship. Our predictor variable is not going to help explain the variability in our outcome variable. The alternative hypothesis is the really interesting hypothesis. It's the one that we suspect is actually true. Otherwise, we wouldn't be conducting the research study in the first place. So the alternative hypothesis is always the opposite of the null hypothesis. So in this case, there is a relationship. So when we're talking about correlations, we're always talking about relationships between variables. So the alternative hypothesis will be, yeah, there's something there to find. There is a relationship. Notice that this is very vague. We don't say there is a strong relationship, or there's a weak relationship, or a positive relationship, or negative relationship. Because really, when we're conducting a research study, we don't know what kind of relationship there is, or even if there is one to find. So we come in and we say, okay, well, there's two possibilities. There either is one, the alternative hypothesis, or there's not, the null hypothesis. And these hypotheses, remember, are about the entire population that you want to generalize your study to. So we will collect our data from our small sample, or hopefully a large sample, from your population. And then we want to look at the data. But just because we see a relationship in the sample doesn't necessarily mean that there's really a relationship in the whole population. It could have just been that we found some people who happen to have certain, data that makes it look like there's a relationship, but in kind of the real world and the whole population, there isn't one. So these two hypotheses are always going to cover all of our bases, all of the possibilities. There either is a relationship or there's not. One of those two things has to be true. There's no other possibility. The second step in our process is to set a significance level, or pick a significance level. And so it's worth talking about this word significance for a moment, because in statistics, we use this word very differently than we do in regular life. So in regular life, we tend to use the word significant to indicate that something is important, like your significant other is important to you. Or if you have a significant event in your life, that's usually something big or something important is happening. In statistics, we don't use this word this way. We use sort of an older meaning of the word. And so really what I want you to think of when you hear significance is, let's do this one, is we want to find like kind of the weirdness level. We want to think, instead of significant, I want you to think weird. So when we're talking about significance levels, so for example, we have our big population, we pull a sample from that population, we look at the data, and maybe we see a sort of relationship there. But keep in mind that since we're working with just a small piece of our population, we're usually not working with, the whole thing, then just because we see a relationship in our samples data doesn't necessarily mean that there really is a relationship going on in the whole big population. It could just be by chance that we see some data that looks like there's a relationship, but it doesn't really reflect the whole population. So we need to establish, if we're looking for a relationship, all right, if I see a relationship in my sample, how big or how strong does that relationship have to be to the point that I'm pretty convinced that, yeah, there really is a relationship in the bigger population? We set a level where we decide, okay, if a correlation of this sample size, if it's beyond this level, then we're going to say, okay, then we think there really is a relationship in the whole population. If it doesn't cross into that level, then we're not convinced. Then chances are not good enough that, that it's not just happening by chance. So in the social sciences, and actually in a lot of the sciences, we use a level, so we call it alpha. It looks like a little Jesus fish, right? So that guy right there is called alpha. And so in a lot of the sciences, and especially in social sciences and business and education, we use a significance level of 0.05. So what this means is that there's smaller than a 5% chance that we would see this particular result in our sample if it doesn't actually exist in the whole population. So really what we're doing is we're saying, okay, so we always start out assuming that the null hypothesis is true. So we don't want to assume something, right? Because if you assume, you make an ass out of you and me, that whole kind of thing. Oops, sorry about that. So we start out, assume that this is true. And then we want to see, is there evidence to the contrary? But we don't want to start out assuming there's any particular kind of relationship because we wouldn't know what that would be. So we start out with no relationship because we know what no relationship would look like. It would look like a correlation of 0. So start out by saying, okay, we assume there's no relationship in the whole population. We take a sample, we look at their data, see if there's a relationship in our sample, and then we determine, okay, is that relationship strong enough that we believe that this null hypothesis is actually not true, that there is a relationship in the whole population? And so what we're doing, this alpha level, it corresponds with something that we're going to call a p-value. And so the p-value is really, generally what the p-value stands for is it's the probability of getting our particular result in our sample. So of seeing the thing in our data, of getting our data and seeing how that is. So the probability essentially of getting our result that we see in our sample if the null hypothesis is actually true. And so I'm going to, if it helps you to remember, because this is one of the most, it's like extremely hard thing to understand in statistics. This is probably the hardest thing for entry-level students to understand from statistics. So if it helps you understand, so our p-value is the probability of our result if the null is true. So if it helps you to remember the acronym PRINT, the probability of our result if the null is true. Because we always start out by assuming that the null is true, and then we try to see, is there evidence to the contrary? So this alpha level what this stands for is we're going to say, okay, if the probability of getting our result, if the null hypothesis is really true and there is no relationship, if this probability is less than 5%, then that means that our result would be really weird, right? There's less than 5% chance of getting our result if the null hypothesis is true. That's a small chance. So we're saying if there's less than a 5% chance of getting our result, assuming the null hypothesis is true, then we're going to say, no, I don't think the null hypothesis actually is true. I'm going to not go with this one. I'm going to choose the alternative hypothesis. I think there really is a relationship in my population. So this 0.05 corresponds to essentially if there's a 5% chance or less of getting our result, if the null is true, then we are going to reject the null hypothesis in favor of our alternative hypothesis. So step 2, setting the significance level. And in this class and generally, that's always going to be this 0.05 or 5%. Somebody at some point decided less than 5% is so unlikely, I don't think it's true. I think the alternative is true. Now, step number 3 is to essentially set our decision stage. So we've got our null hypothesis and our alternative. We start out, assume the null is true. We've got our data. We've decided if it turns out that the probability of getting our data, our result, is less than 5%, if that null hypothesis is true, if it's less than that, then we're going to reject the null hypothesis and go with the alternative. So the decision stage we use to basically help us identify our cutoff points. And what I mean by cutoff points is we want to establish, okay, if we're saying 5%, what does that correspond to in terms of an R value? So if I have an R value, how do I know if it's below 5% chance of getting that if the null is true or above 5% chance, right? So this third stage, this third step is to help us do that, is to identify at what point are we going to cut off that 5% so that we know that if it's beyond this value, there's less than a 5% chance of that happening, and we reject and go with the null hypothesis. So what we're going to do in this case, so if you're doing it by hand, it's different than if you're doing it on the computer. If you're doing it on the computer, we almost sort of just skip this decision stage step. But because we're doing this by hand, really what's going to help us to identify that cutoff point is to identify the critical R value. And this is typically written as, sorry, that is wrong. Typically written as R with crit down below. So that's our critical R value. Okay, so here is a table that has, as you can see, critical R values. Now when I say R corresponds, it's just the symbol that we use to represent Pearson's correlation coefficient. Some guy named Pearson, actually my maiden name, wasn't me, it was a long time ago, came up with this way of calculating to determine if there's a relationship and kind of the strength of the relationship. So we have this table that has all these critical R values. This is very confusing to read, right? Looking at this, it doesn't really help to show us what we need. So, but this is what we're going to be using. And just to explain a little, so we're never going to be using one-tailed tests in this class. So you always want to just ignore that top part. And I crossed out this part because we're not going to do two-tailed. This always in psych, that's actually supposed to point to that two-tail. Always using two-tailed. We'll talk about what that means kind of in the future, but for now, just know two-tailed. Then this row here is level of significance. So this is that step 2 that we just did. So when we say level of significance, we are going to be using 0.05. And so you'll notice what's going on with this table is it's just going down and then it wraps around. So 1, 2, 3, 4, 5, 19, 20, it wraps around to 21, 22, and so on. So we are going to be looking at the values in this column only because our significance level is 0.05. The thing on the left-hand side, these to tell you which row you want to look at to find your critical R value, these stand for degrees of freedom. And degrees of freedom it's a very difficult concept to understand, but for correlation, you'll want to know that degrees of freedom is equal to n minus 1, where n is your sample, n minus 2, where n is your sample size. So if we have 50 people in our sample, then our DF, degrees of freedom, is 48. If we had 3,012 people in our sample, our degrees of freedom is 3,010. So however many people you have in your sample, subtract 2, and that's your degrees of freedom, and that tells you which row we're going to look down. So if we had 42 people in our sample, then our degrees of freedom is 40, and we would use this critical R value here. So it all depends on how many people are in your sample. So back to our notes. So we want to identify our critical R value. So we know that when we get the R that goes with our data, is it beyond that or is it not beyond that? Right? And so when we get down to step 5, I'll kind of reiterate, how do we make this decision? Now, step 4 in our process is to use our sample to calculate the statistic, right? So remember, samples have statistics, populations have parameters. So we're going to use our sample and calculate whatever statistic we're interested in for that particular analysis. In our case, we're going to calculate an R value because we're looking at correlation. So we would calculate, okay, our sample has an R of something. And usually we call this the observed R, just to keep things straight, not to confuse it with the critical R. Critical R sets the boundary of where we're going to decide to reject the null hypothesis or not reject the null hypothesis. The observed R, which is typically written as R observed, is the R that goes with our actual sample. Then step 5 is to make a decision. And really it's make a decision about our null hypothesis. So this can look kind of 2 different ways, depending on if you're doing it on the computer or if you're doing it by hand. So if you're doing it by hand like we are here, then this means we're using the critical value sort of method of making our decision. So if our observed R that we got from our sample is bigger than the critical R that we got from the table, then this means our correlation from our sample is so big or so strong that there's less than a 5% chance of getting it if the null hypothesis is true. So in this case, we would reject the null hypothesis and go with the alternative. And we call this, when we have a result that matches this, that allows us to reject that null hypothesis, we say it is significant. This is a significant finding, meaning that it would be so weird to get an R value this big from our sample if it doesn't really exist if a relationship doesn't really exist in the population. That would be so weird that we don't think that the null is actually true. So we're going to reject it and say, this is significantly weird that we believe that there is a relationship in the population. Now, if our R value that we got from our sample is not bigger than that critical R value that we got from the table, then we do not reject. People often want to say, oh, that means that you accept the null hypothesis. But remember, in science, in research, we don't really know the answer. So we never say that we accept the null hypothesis, there is no relationship, because maybe we just didn't find it. Maybe something went wrong somewhere and we just didn't see it. We didn't have the right people, or it's a really small relationship, and so we need lots of people to see it. So we would just say, well, in this case, our evidence is not strong enough. We do not reject the null hypothesis, and we call this not significant. Now, if you're doing this on the computer, then basically it helps you skip some of these middle steps. And so we have kind of an equivalent to each of these for if you're using the computer. So when you're using a computer, it's going to spit out a p-value. And that p-value is what we're going to use. So on the computer, if our p-value is less than 0.05, then that means there's less than a 5% chance of getting our result if the null hypothesis is true. So if there's less than a 5% chance, which is what we set our alpha at, then in this case, we reject the null, aka it's a significant result. If the p-value we get is not smaller than 5%, that means there's a 5% chance or higher that we could see our result if the null hypothesis is true, well then the null hypothesis might be true. We don't have good enough evidence to decide it's not true. So in this case, we do not reject, aka we would say it is not significant. So we're going to take some time to go through and actually do this by hand. So here's our example. We have a random sample of 7 junior high students, and each student is given both a math test and a spelling test. Test at the 0.05 significance level, so there's our alpha level. So step 2 already done. We want to test whether their scores on the math and the spelling tests are related. Or are these two separate things? Doesn't matter what their math test score was, doesn't inform us about their spelling test score, and vice versa. So what are our null and alternative hypotheses in this case? So in this case, the null hypothesis would be that there is no relationship between their math and spelling scores. And again, we're not talking about just these 7 students, we're talking about the whole population of students, whether that's this class or this school or students in general, 7th graders in general, right? So when we say there's no relationship, we don't mean just among these 7 people, we mean in the whole population. The alternative is just the opposite of that. So instead of there's no relationship, we would say there is a relationship between math and spelling test scores. So one of these two cases has to be true, and we're going to calculate the R value for this sample of 7 students and say, is that R value that we get, is that big enough that we think that this one, the null hypothesis, is not actually true, that it is the alternative, that there is a relationship. So our next step is to calculate it, break it down. Here is the formula for calculating R, or one of the formulas for calculating R. To do this formula, we would have to have, remember the S stands for standard deviation. We would have to have the standard deviation for their math scores and for their spelling scores. Since we don't already have those calculated, it's actually going to be easier to do this version by hand. It looks even uglier than the original version, but this is going to be, it's an equivalent version that will get us there, but it's easier to do if you're doing it by hand. So let's get going. So I've kind of color coded. You can see down here at the bottom, I've just repeated this same formula, and then I've color coded of where we're going to get these values. so that we can just plug them in and then combine. So the first step, so I've already set up the table. We've got our 7 students, our 7 math scores. In this case, math is X, and there's 7 spelling scores, spelling being Y. And so the first step is to find the mean math score and the mean spelling score. So I'm going to pull up my calculator over here. All right, so I'm going to do add these all up first. 15 plus, nope, fat finger, sorry. 5 plus 16, 10, 11, 3, and 12. So I got 72. And since there's 7 students here, then I'm going to divide by 7 to get my mean. In this case, my mean is 10 point, oh, where did it go? 10.29, round that one up. Okay. Now let's go ahead and do the same thing for Y. So for Y, I have 13 plus 6 plus 14 plus, plus 13 plus 11 plus 5 plus 10. And I really recommend, if you're, get 72 again, I recommend if you're doing this by hand, always do it until you get the same answer twice. So like I really should add these up again just to make sure it really is 72. And my fat fingers didn't just hit the wrong button. But I've done this before, so I know it's 72 and I know I got the right answer. So, so 72, again, we have the same 7 students, so 72 divided by 7. We actually, in this case, have the same mean. This is not always the case. Why are you moving my numbers all around, computer? That should go there, and anyway, 10.29 goes in here all together. Yes, okay. So in this case, our 2 means actually are the same. That will not be the case in every data set. It just happened to be that way in this one. Now, this next column over, this x minus x bar, that's this part of the equation. So this just means take each of your values and subtract the mean and put it here. 15 minus 10.29 equals 4.71. So 4.71 goes here. Since I'm just going to scan through, no other 15s, otherwise I could put those in at the same time. Okay, now how about 5 minus 10.29, and we get negative 5.29. Any other 5s? Yep, so I'm just going to put the same thing. Since these have the same mean, it actually makes it a little easier because 5 minus 10.29 is still going to be negative 5.29. So plug that in. Then up next, 16 minus 10.29. We're going to get 5.71. No other 16s, okay. 10 minus 10.29 is going to be minus 0.29. So then there's another 10 over here, so I'm just going to save myself a little time, put it in there. 11 minus 10.29. You see, this gets really tedious really fast. Got another 11 over here, put it there. 3 is negative 7.29. No other 3s. How about 12? And a couple more, so 13. This is why, folks, this is why we use computers. Because this, so if 13 is 2.79, then 14 is going to be, or 3.71. 6. All right, minus 4.29. Okay. So for this next step, we are going to square each of these. So 4.71 squared is 22.18. And then 5.29 negative squared, 27.98. 5.71, 32.60. And people always ask me when I'm doing this about rounding. Honestly, if you round a little bit, it's not going to make a big difference to the overall calculation. But going to 2 decimal places is probably best. So 0.08, 0.7, 0.50. 7.29. And again, I know that whether it's positive or negative, it's going to come out positive when I square it, but 53.14. And then the last one, 1.71 squared, 2.92. So to save myself a second, let me see if there's any of these are repeats. So the 5 is a repeat, so I'm going to put my 27.98 here. The 10 is a repeat, so I'm going to put my 0.08 in. 11's a repeat, so I'm going to put 0.50. And I think that's it for the repeats. Okay. We're going to do the 2.71 squared is 7.34. Then 4.29 negative squared is 18.14. 3.71 squared, 13.76. And finally 2.71 squared, 7.34. You see how long this takes. And this is only 7 students. Imagine if you had like a sample of 500 people. So now what I want to do is I want to add all of these together, right? So we took x minus the mean, then we squared them all. Now I want to do the sum of squares. That should sound vaguely familiar. So the sum of squares down here. So adding together 22.18. 7.98 plus 32.6 plus 0.08 plus 0.5 plus 53.14 plus 2.92, and I get 110.4. Now this side, 7.34 plus 18, nope, 0.14 plus 13.76 plus 7.34 plus 0.5 plus 27.98 plus 0.08 equals 75. What was that? 14.14. Okay. So next up, so we've got those. So this last column, so if you look, we've now got the green part. So we've got this guy, which is the 110.4. We got this guy, the sum of those squared deviations is going to be 75.14. So I may as well put those in here since I already have them. And since they're just listed next to each other, we're actually going to multiply them together. So what we need left is the top. So the top is telling me take the deviation for the x for that student and multiply it by the deviation of the y for that student. So I'm going to take this column and multiply it by the value in this column to get here. So 4.71 times 2.71. 12.76. Then we have 5.29. Here, the negative does matter in case they're both not negative. So 5.29 times 4.29 negative, 22.69. Next we have 5.71 times 3.71, 21.18. Next up, we've got, let's see here, negative 0.29 times 2.71. That one's positive, so we get negative 0.79. Next up, 0.71 times 0.71. Okay, so 0.71. 0.50, right? Because this is 0.71 squared, so 0.50. Now, negative 7.29 times negative 5.29, 38.56. We're almost done. And finally, 1.71 times 0.29, and that one's negative. So we get minus 0.49. That should be 50, but again, a little bit of rounding up or rounding down is not going to make a huge difference in the end. Okay, now we've got these, we need to add them up because that's what that symbol means. All right, let's take these guys out here. So 12.76 plus 22.69 plus 21.18 minus 0.79, because the minus there, plus 0.5 plus 38.56 minus 0.49. And I get 94.41. So that one comes in on the top. So I'm first going to do this step, the multiplication. So 110.4 times 75.14, 8925.46. 8925.46. Got it. Okay, so then we've got the 94.41 on top. So let's do this division, or first let's do this square root, right? So take the square root of that guy, 91.08. I messed up somewhere. Where did I mess up? I can tell already I messed up. Because if I do 94.41 divided by 91.08, it's over 1, which is impossible with correlation. So I made a calculation error somewhere in here. This is why we use computers. I am not about to do it all over. I know what the actual answer is because, you know, I came up with this problem and I did it before. The real answer is 0.91. So I messed up somewhere. You don't want to see me do it over again. I don't want to see me do it over again. We're just going to go with this, and this will be a lesson on why I don't make us do stuff by hand in this class, because it is so easy to make a small mistake and mess up somewhere. This is why we use computers. Let's use the technology that we've got. So Let's go with this guy. Oops. Nope. Something's wrong here. I don't remember. I should have my my key loaded, but I don't, unfortunately. Oh, please don't move to the next page. Okay. So we're actually doing things a little out of order here, right, of the steps that I said, because that was really step 4, calculate the statistic, right? Step 3 would be, what is our critical value of R? But it just fit better on the page the other way. Okay, so what is our critical value of R? We're going to look that up in our R table. So to look this up, we need to know what is our sample size so we can calculate our degrees of freedom. So remember, our sample size is the number of people in your sample. So the number of people in our sample is 7. So then this means our degrees of freedom is equal to 7 minus 2, because we're using that n minus 2 formula for this. Our degrees of freedom is 5. So on our paper, we want to look for degrees of freedom equal to 5, which is right here. We know we're going to be looking in the 0.05 column because alpha is 0.05. That means our critical value is this guy right here, 0.755. So my critical R value equals 0.755. And finally, we get to stage 5, step 5, where we get to make our decision. So remember from up here, way up here, step 5, if our observed R, our calculated R, the one we did by hand that I messed up, that is actually 0.91, if that is higher than the critical value from the table, then we're going to reject the null hypothesis, because that means that our R value is so big that it's really unlikely to have occurred if the null hypothesis is really true. If it's not bigger than our critical value from the table, then we're not going to reject. We'll say our evidence is not strong enough. We can't conclude. We got to just keep assuming the null until we get any better evidence that it's not true. So our decision here, we want to look at, we're comparing if our observed R is bigger than our critical R, then we're going to reject, just to have it here. And then if it's not, we are not going to reject. So what was our observed R? That's the one we calculated that I messed up. That is actually 0.91. So 0.91 is our observed. Our critical one that we looked up in the table is 0.755. Which one is bigger? No, this one's bigger. So Pac-Man's going to eat it. All right, that helps you remember. So if our observed R is bigger than our critical R, we are going to reject the null hypothesis. In other words, we would say that it is significant.
So what this means essentially is that, okay, we assume there's no relationship in the whole population between these things. Then that means the correlation in the population would be 0. We got a sample that has a correlation of 0.91. If the real population correlation is 0, it would be super, super weird to get a correlation as high as 0.91 in our sample. And it's so weird that it occurs less than 5% of the time. So there's less than a 5% chance that we would see this result if there's no relationship in the null hypothesis. And that chance is so small that we're going to reject it and say, nope, I believe there is a relationship in that hypothesis. Or sorry, there is a relationship in the population. Finally, define the relationship between the variables in this problem based on all your information. What does it all mean in the context of the problem? So we're going to start getting into how do we officially write up our results. And so this will show you just very briefly, this isn't, so we were doing this analysis really attempted to see if there was a relationship between their students' math scores and spelling scores. So we would conclude that there is a significant, it's a strong positive relationship between students, let's just do it that way, students' math and spelling scores. And then this next part has to do with what we call APA style, American Psychological Association style for reporting results. So we would do comma, R in italics for correlation. In parentheses, we are going to do why won't it write? We're going to do the degrees of freedom. So in this case, our degrees of freedom was 5. And then our correlation that we got with that degrees of freedom as 5 was 0.91, or what we should have gotten. And then we're also going to say that P, the probability that we would get this result if the null hypothesis is true in the whole population, that probability is less than a 5% chance of happening. So we have that it's significant, and we know this because there's less than a 5% chance of it happening because our observed value up here was much higher than the critical value. We know it's strong. We're going to get more into this, but we're going to have certain cutoff points to determine what's a weak relationship, what's a moderate relationship, what's a strong one. This happens to be strong. It's very close to 1. This is a strong relationship between them. How do we know it's positive? Well, our answer didn't come out negative, therefore it's positive. So we're saying there's a significant, strong, positive relationship between students' math and spelling scores. We know this because the R value we got with 5 degrees of freedom was 0.91, and the probability of that happening, if the null hypothesis is true for the population, is less than 5%. So therefore we conclude null hypothesis, probably not true. We're going to go with the alternative that there is a relationship. And since our sample shows a strong positive relationship, we're going to think probably the population, the same thing, strong positive relationship. So thanks for sticking with me through all the difficulties. I hope you learned something. We will keep going over this. So if this was hard, it's supposed to be hard. It's hard for everybody at first. So stick with me. We'll go through this over and over and over again. And I'm hopeful that by the end of this class, you'll understand what that p-value stands for, and you'll be able to interpret it and what it means. So thanks, and I'll see you soon.